you actually do have just an inherent advantage because you don't need to go through muscle. So the question is just how much faster can you make it? And we're already, faster than, what you would do if you're going through muscle from a latency point of view. And we're in the early stages of that. I think we can push it. Sort of our end-to-end latency right now from brain spike to cursor movement is about 22 milliseconds. If you think about the best mice in the world, the best gaming mice, that's about 5 milliseconds-ish of latency, depending on how you measure, depending how fast your screen refreshes. There's a lot of characteristics that matter there. But yeah, and the rough time for like a neuron in the brain to actually impact your command of your hand is about 75 milliseconds. So if you look at those numbers, you can see that we're already competitive and slightly faster than what you'd get by actually moving your hand. And this is something that, if you ask Nolan about it, when he moved the cursor for the first time, we asked him about this. It was something I was super curious about. Like, what does it feel like when you're modulating, a click intention or when you're trying to just move the cursor to the right? He said it moves before he is like actually intending it to, which is kind of a surreal thing and something that, I would love to experience myself one day. What is that like to have the thing just be so immediate, so fluid that it feels like it's happening before you're actually intending it to move?
Yeah, I suppose we've gotten used to that latency, that natural latency that happens. So is currently the bottleneck the communication? So like the Bluetooth communication, what's the actual bottleneck? I mean, there's always going to be a bottleneck, but what's the current bottleneck?
Yeah, a couple things. So kind of hilariously, Bluetooth low energy protocol has some restrictions on how fast you can communicate. So the protocol itself establishes a standard of, the most frequent sort of updates you can send are on the order of 7.5 milliseconds. And as we push latency down to the level of sort of individual spikes impacting control, that level of resolution, that kind of protocol is going to become a limiting factor at some scale. Another sort of important nuance to this is that it's not just the Neuralink itself that's part of this equation. If you start pushing latency sort of below the level of how fast screens refresh, then you have another problem. Like you need your whole system to be able to be as reactive as the sort of limits of what the technology can offer.
Yes.
Like you need the screen, like 120 hertz just doesn't, work anymore if you're trying to have something respond at something that's, at the level of 1 millisecond.
That's a really cool challenge. I also like that for a t-shirt, the best mouse in the world. Tell me on the receiving end, so the decoding step. Now we figured out what the spikes are. We got them all together. Now we're sending that over to the app. What's the decoding step look like?
Yeah. So maybe first, what is decoding? I think there's probably a lot of folks listening that just have no clue what it means to decode brain activity.
Actually, even if we zoom out beyond that, what is the app? So there's an implant that's wirelessly communicating with any digital device that has an app installed.
Yep.
So maybe can you tell me at high level what the app is, what the software is outside of the brain?
Yeah. So maybe working backwards from the goal. The goal is to help someone with paralysis, in this case Nolan, be able to navigate his computer independently.